Greetings to Madam Salavioti and my dear course mates. We are from Group 2 and we will be presenting our operating system project presentation. My name is Ungan Leo with the metric number 97435. I will be sharing about what is our project title. Our project is entitled Performance Evaluation of Round-Robin Scheduling Algorithm with Varying Time Quantum. Next up, I'm going to introduce our other members, which are Whitellmina Vatha, Nur Imanina, myself, Dayang Nur Batrisyia, and Ahmad Afiq. Our project objectives are implementing the round-robin scheduling algorithm, evaluating the scheduling performance, and also enhancing understanding of scheduling concepts. By implementing, we mean by developing a functional C program that accurately simulates the round-robin CPU scheduling process. By evaluating scheduling performance, we calculate and analyze key performance metrics such as turnaround time, waiting time, and the number of interrupts to assess the algorithm efficiency under various time quantum values. And lastly, we provide an interactive tool that demonstrates how round-robin scheduling works, helping users understand its role in fair CPU resource allocation and system responsiveness.
Hi everyone, my name is Whitellmina anak Layong with metric number 86051, and I'll be demonstrating the code for time quantum values ranging from 5 to 30. We will see how the completion time, turnaround time, waiting time, and interrupts are affected by different time quantum values. Before we start, let me briefly explain some key functions in the code. The first function that plays a crucial role is read job from CSV. This function reads job data from a CSV file, including details such as job number, birth time, and arrival time. It saves this information in an array of job structure for scheduling. This is our group job list file named joblist02 since we are group 2. From this file, we calculated the birth time for each job and compiled the data into job go2.csv, which include the birth time and arrival time for all jobs. We use a specific function to compute this birth time, and then we gathered the birth time and arrival time into job go2.csv. And this CSV file is then read by the read job from CSV function. The next function is reset job. This function is to prepare for new scheduling round by resetting all job details like completion time, turnaround time, waiting time, remaining time, and interrupts. Now, the most important function is round robin. This is where the round robin scheduling algorithm is implemented. It processes job by checking if they need more time or can finish within the time quantum and tracks the number of interrupts. And lastly, the display result function is to print the scheduling result, including the job details. And it will also print the average turnaround time, average waiting time, and the total number of interrupts for all jobs. Now, let's test the algorithm for time quantum values from 5 to 30. First, with time quantum 5, here we can see that the job process and the number of interrupts is quite high. This is because with a smaller time quantum, the CPU has to preempt job more frequently and leading to more interrupts. And we also notice that the turnaround time and waiting time are higher due to more context switches. And this is the average result for time quantum 5. Okay, next, let's try time quantum 10. As you can see, the interrupts have decreased compared to time quantum 5, and the jobs are being processed with fewer preemption, which result in a lower waiting time and turnaround time. And this is the average result for time quantum 10. Next is time quantum 15. And we see a further reduction in interrupts and jobs are processed more efficiently. Let's continue with time quantum 20. Here with time quantum 20, the jobs are even more efficiently processed, and the system seems to balance the need for preemption and job execution better, and leading to improve the turnaround time. This is the average result for time quantum 20. Next is time quantum 25. We see that the system is performing very well with fewer preemptions and much lower turnaround time. The jobs are complete quickly with minimal interruption. And this is the average result for time quantum 25. Next, time quantum 30. With a time quantum of 30, the system performed even better with the lowest number of interrupts and the fastest turnaround time. However, this also means the jobs may not be preempted frequently enough for very short tasks. And this is the average result for time quantum 30. Okay, that's it from me, and I will pass it to Afiq Adzly. And thank you.
My name is Afiq, and I will be demonstrating how our code performs with different time quantum values ranging from 35 to 60. The round-robin scheduling algorithm works by allocating a fixed time quantum for each job in a cyclic order. When a job's time slice expires, it is preempted and the next job is executed. Let me please run the code. First, let's start with a time quantum of 35. Our program reads job data from job go2.csv file, which contains the job number, burst time, and also arrival time. As we see in the output, jobs that requires less than 35 units are completed in one cycle. Jobs with higher burst times are interrupted and continuous in the next cycle. Notice how the number of interrupts may vary depending on the job's burst time and how efficiently the system handles job switching. Next, let's run the code with a time quantum of 40. Comparing the results, we observe fewer interrupts compared to a time quantum of 35. This is because larger time slices reduces the number of preemptions, allowing jobs to complete in fewer cycles. So now let me run for the all remaining time quantum. It's for the 45, and here is 50. Here's the 55. And last but not least, time quantum of 60. Now, as you can see here, for the time quantum of 45, further reduction in interrupts, longer jobs complete more efficiently. And for time quantum of 50, average turnaround and waiting times decreases as jobs are completed faster. And for 55, and also 60, interrupts are minimized and the system performs close to a first-come, first-served scheduling approach since the time quantum is large relative to job burst time. So now let's discuss the average metrics for each time quantum. For smaller time quantums like 35 and 40, we see higher average turnaround and waiting times due to frequent job switching. As the time quantum increases, average turnaround and waiting time decreases. However, if the time quantum becomes too large, it might lead to inefficiency in multi-user system. To summarize, smaller time quantum increase fairness but result in higher overhead due to frequent context switching. Larger time quantums reduce overhead and improve efficiency for longer job but can lead to delays for shorter jobs. That's all for me. Thank you.
Hi, my name is Dayang Nur Batrisyia binti Ramzi, holding the card matrix number 97353, and I am going to present the comparison charts. The first comparison chart is turnaround time versus time quantum. Turnaround time represents the total time taken from the submission of a process to its completion. As the time quantum increases, a trend indicates fluctuations in turnaround time. Notably, smaller time quantums led to slightly reduced turnaround time initially, but larger quantum values stabilize the turnaround time at higher values. The next chart is waiting time versus time quantum. Waiting time refers to the time a process spends in the ready queue waiting for CPU allocation. The graph demonstrates a trend where smaller time quantums result in higher waiting times as the CPU switches context frequently. Increasing the time quantum reduces the frequency context switches, leading to marginally lower waiting times. However, beyond a certain quantum size, the reduction plateaus. Last but not least, number of interrupts versus time quantum. The third chart visualizes the number of interrupts occur when the time slice for a process expires and the CPU switches to the next process. The graph shows that the number of interrupts is inversely proportional to the time quantum. Smaller quantums result in significantly more interrupts due to frequent context switching. while larger quantums reduce interrupts as processors allow more uninterrupted CPU time. That is all from me. Thank you.
My name is Nur Imanina binti and my metric number is 97692. I will be presenting the evaluation of the best time quantum for round-robin process scheduling as well as our recommended time quantum for this project. Let's begin with turnaround time, which measures the total time taken by a process to complete. The lowest turnaround time occurs at a time quantum of 50, while the highest turnaround time is at 55. Next is waiting time, which tracks how long processes wait in the queue. The lowest waiting time is also at a time quantum of 50 and the highest waiting time is at 55. Lastly, the number of interrupts decreases as the time quantum increases. The highest interrupts occur at 5 while the lowest are at 60. By balancing these metrics, time quantum of 50 is recommended for optimal performance. It achieves the lowest turnaround time and waiting time significantly reduces interrupts to 2212 and strikes the best balance between responsiveness and CPU efficiency. In summary, a time quantum of 50 is the most effective choice for process scheduling. That's all from us. Thank you.